Hernán Valdez. I am a student of Applied Computer Science. Yeah, sorry, see you also the mini screen in the side? Or is the all these slides?
No, we have just one
Do I need to
slide.
minimize something, or is it only this slide?
We have just one major slide.
Okay, because I have like a pop-up in my screen. I didn't know if you can see it too. Okay, so my name is Hernán Valdez. I'm a student of a bachelor program in applied computer science at the Technical University Freiberg. And the topic that I'm going to present is training of an object detector and the impact of image size as an input parameter. So as a matter of context, last semester, me and fellow students participate in a project-oriented class in the Technical University Freiberg with Professor Sebastian Zug. The class was software technology, and it was heavily inspired and contextualized at the RoboCup at work competition. And all the results and numbers that I'm going to present are not the result of a single person, me, but instead of a team of students. It was Juliana Biesinger, Miriam Henel, and me, Hernán Valdez, that worked together to solve a problem, a given problem. And the problem was the generation of an object detector. The problem should be solved in 3 stages. First was to be able to classify and localize objects. Second was to count the number of detected objects. And third and last was to output these detections following the Cocoa annotations style through a JSON file. So first of all, about object detectors. Very broadly speaking, there are 2 big groups of object detectors that we found as in the moment that we were researching for our class. And there were the 2 stage detectors and 1 stage detectors. As you can see in the picture, both of them share some sort of same kernel, and the 2 stage detectors had like an extension. So in the 2 stage detectors, that are the older one models, you can find names like RCNN for relations of interest, convolutional neural networks, and the whole family of different RCNN networks, be, for example, fast RCNN, faster RCNN, and other variations. And for example, for 1 stage detectors, you can find some algorithms and solutions like YODO, SST, that's a state for single shot detector, and RetinaNet. So as an example, for our 2-stage detector, we have schematics for our RCNN, and we have a first step that is our input image. Once that we have our image, we proceed to select different regions through an algorithm. In this case, the selective algorithm that consists in reading different blocks of information around the whole picture, then through an iterative process, just like take in account all the blobs that have similar qualities, and after that you generate 2,000 different regions where you can say with some sort of security that there is a possible object to be detected. So once that you have all of these regions that you can see in the step 2, then you proceed to warp the region. That means that we square the region proposal, that we are not so sure that there is an object there, but because of the blocks, we have some sort of security that there is probably an object, and we proceed to use this warp region as an input for a convolutional neural network. And after that, we can classify the different regions. All this process is very slow for example, for an activity that requires real-time image detection, but it has very stable and good results. And it can also detect small elements in your image, and it doesn't also have problems with images that are in the, for example, one image is very close to another. Because of the very slow process, and there are newer algorithms, for example, the fast RCNN and faster RCNN, that they actually experiment or evolve this algorithm, and they edit the step 2. And for example, in the faster RCNN, they remove completely this selective algorithm or selective search algorithm, and they use new neural networks, so that it's like two neural networks, one for searching the different regions of interest, and the second one is to confirm or to classify of what for an object is every single of these regions of interest. And we have a different approach that's, for example, in the case for a one-stage detector, that we have the famous algorithm YOLO, or you only look once. And it consists that you have the image, like the dog with the bicycle, and once that you have the image received, you generate a grid, homogeneous grid of mini squares in the whole image. And for every single cell of the grid, you proceed to calculate which class of elements could be present based on the different bounding boxes that was given at the beginning of training. So the image is only once processed. You don't need to read the pixels of the image a second time, because you have generated a new vector with all the different grids, with all the different classes and the different probabilities for every single grid. And once that you have every possibility, one had done, like in the upper picture, a lot of different boxes with different probabilities. After that, we take a max probability or a max consideration, in which we only took in consideration the max values. And after that, we can consider that they are not like 5 or 10 dogs in this picture, but only once. So one big problem that the first generations of YOLO image recognition has, because of the algorithm, is that if you have two, for example, in this picture, two dogs very near with each other, there is a probability that the algorithm thinks that actually one of them is only the dog and the second one is like an error from the calculation, that maybe one dog had a probability of 0.9 and the other dog had a probability of 0.89. So there is only going to be show one of the dogs. So that was one of the problems of the very first version of YOLO. Actually, there is a lot of new versions of YOLO, and there's a little controversy between YOLO version 4 and YOLO version 5, that they were launched very close. And the last version from YOLO version 4, that is like the inheritance of the original YOLO, was launched in this year in April, and it shows that in comparison with another methods, like for example 2 stages, shows an average precision a little lower, but the number of frames per second that it can reach is very high in comparison with the other. So because of this, we took the decision to proceed with these algorithms because it is very practical for a real-time object detection instead of static analysis in which you want, for example, in Google Photos, only classify or see the names of particular persons, for example, in a picture, not in a video. So one of the big benefits of YOLO is that there is a lot of implementations, open source implementations in different language and different web framework, in different machine learning frameworks, for example, in PyTorch and TensorFlow. And we took into consideration mainly because of the good documentation and the easily implementation of the company Ultralytics that had an open source project with the name YOLO version 3 that you can find in the link below. But this repository with the name YOLO version 3 actually had the configuration files also for different types of YOLO. So it's not only restricted to YOLO version 3, but also to YOLO version 4, that it was we actually ended using in the project. So about the dataset, as I mentioned in the context before, at the beginning, it was this project heavily based at the at work competition, and the Otto von Guericke Universität Magdeburg had uns had very gently shared big data sets of pictures, and it consists of first label and crop images, like in the left side, and also raw images with a big JSON file with all the annotations needed to train. So based on these two different data sets that at the end it is the same, but one is only with images that are labeled and or separated and cropped, and the ones that are raw images and with labels and bounding boxes, we create 3 derived data sets. One, a classification data set. So this is already cropped, and in the images of the different, the sizes of the different images are heterogeneous. Some are very big, some are very large and thin. So that adds some complexity. And we have a second derived dataset, that is the detection dataset, and that is the pictures or the images with the original size. And after that, we want also to experiment and test with a little of pre-processing in our dataset, and we generate the small detection dataset that is 5 times smaller than the original size. So at the end, we could receive very good results for both the detection and for the small detection, not for the case of the classification. So as of metrics to use with YOLO, we have actually different metrics. One is precision. And in this case, for the precision, we take we try to search how accurate is your prediction. And for the recall, we try to search how good how good are you finding all the positive results. So, and we have an average precision. That is also going to take into consideration about how are all the precisions for the bounding boxes were detected. So taking this in account, we have a automatically generated graph from the repository from Ultralytics. And in blue is the results of the classification. In orange, the results from the detection datasets. That means the original pictures. And in green, the results of small detections datasets. So what we found was that the tests were done with only with original sizes, but applying the weights of different uh, of models trained with different size of pictures. But independently of how big the picture was, we found that between the detection and small detection, the difference in precision is very small when we compare with the training time. So we have access to a very good computer, a DGX2 container that we could use during the semester, but it was a really good computer, but independently of this, the task training, the training for the detection dataset was still 67 hours long. And for us, that we were just starting with machine learning, was a very long time and really frustrating, because you don't need to, you you cannot stop simply the process and try to analyze the data, because you need to wait until the end to just to confirm the results. So we saw that there's a decrease in the average, in the mean average precision for the small detection and the precision, but the time that it took to train with the small detection was considerably lower in comparison with the detection. And we have in the other side the classification datasets that we were trying to train a detection system only with the classification pictures. So one of the possible errors that we think that generate these incongruences between the classification and the detection datasets are that we needed to decrease the batch size for the training in the case for classification. The size of the picture was, or the area of the pictures in general were lower, but we needed also to use to decrease the batch size. That could be because the YOLO training model is very flexible, and it does automatically a pattern of all the pictures. So every single picture had a different size, and the training system needed to do an extra pattern for every single picture, that it had an extra overhead, and there was a lot of wasted place in it. So we think that this decrease of the mean average processing could be also because of this factor, that there was a lot of wasted place in comparison with the other, and also because that in this classification system there were any empty images, so that the train didn't have any kind of feedback for the case that there are any object present. And in the detection and small detection, there were the cases present in which there were empty images. So about the conclusions, I said before, YOLO is very flexible. It allows to use any kind of image size, but I would recommend to use an uniform type of size for every image, independently of the size of the training neural network that you are going to set as a higher parameter, and thus that the shrinking of the images as a pre-processing process in the learning pipeline can generate a boost in the training time, and it can help in the process, in the learning process or iteration process, maybe not in the end case process with the end wave, but in the moment that you need to iterate or very quickly or change parameters, and maybe you don't want to wait 3 days until the results are there. One simple trick like pre-processing with the library Pillow from an OpenCV for Python, and they are like 5 lines, and you can decrease the training times immensely, and not with a very high cost in the different parameters like the mean average precision and also the precision subs. So thank you very much for your attention. This was my presentation. Any questions?
Could I, thank you for the presentation. Can I take a look at slide 14, please? Okay. Did you had any problems with M30s and M20s being recognized at each other? Oh yeah, in the right picture, and the button. Yeah, I just wanted to check if this problem persists. We also have this problem.
Do you have also this problem?
Yeah, we had it. I don't know if we also solved it by now. Our vision guy is not here yet. Okay, no, I just wanted to check. Thanks.
we share the same pain.
Yeah.
Okay. And the same dataset, I think.
Yeah, that could be true.
This is an interesting point. The dataset we friendly received from O4GU, and it was a motivation to aggregate data sets from different teams in order to avoid a painful aggregation process that have to be realized individual by each team. Probably I sent a mail in the beginning of the pandemic situation. It's a GitHub repository that is available in our at work link, and here we explained the structure and documented the data set. I think it's still downloadable, and probably we find some other interested teams that are that will support us, or they will support this idea by individual or by their personal data, labeled data from different competitions. On the other hand, it would be really interesting to know, to learn more about the autonome script for Blender for an automatic generation based on simulation inputs. Let's keep this in mind and try to start to develop a common strategy. I guess current time it's not necessary to collect penalties due to the fact that an object was not recognized correctly. The grasping process is complex enough.
Yeah. So we're talking about large data. Do we have an infrastructure for that? Like, no.
We simple prepared a web space from our university, and the dataset can be downloaded there. I guess your collection is 1.5 gigabyte size.
Yeah, okay.
It's not perfect, but of course it works fine for a limited number of users.
Yeah.
Yes, feel free to contact me if you have any additional ideas or the questions how to integrate your material here. The other teams will be very thankful for this. offer. Okay, I think we have reached the last step of the first day. I'm convinced that especially the new teams were able to